Hello again. For this video, some examples about this superposition principle, and we revisited undetermined coefficients method. Uh, kind of, um, it, this is as I mentioned in the other video, can be used for higher order, but we're using here second order, and it is for linear equations and with constant coefficients. So that's important to know, because until this stage, that's what you've seen. And if you're interested in other cases, we will get to that and we'll see in other videos. Of course, the other idea is a general solution can be built by having a particular solution based on the non-homogeneity f of t, and adding to it the general solution to the homogeneous di differential equation that is, of course, associated to this differential equation. And of course, on your notes after the previous video, you probably written that if I have this exponential polynomial, this is how I'm going to build the particular solution. And if I have this with cosine or sine or such combination, then this is how I'm going to build the particular solution. And let's look now into examples and we get to that. So first example is just, let's say you're given a solution to this differential equation. And you're given a solution um, to this differential equation. Notice the left-hand side is the same. The non-homogeneity is different. To understand now just kind of a superposition principle, let's say find the solution. Let's say you have now the left-hand side is the same, but the right-hand side has this. This is where the superposition principle comes to be helpful, since we already know what the solution is for if we have sine of t. Then notice here it's just 3 times sine of t. So the solution is going to be 3 times cosine of t. Right, so you see just 3 times, and this is the solution there. So it's just going to be that. Let's do another example. So let's say this is the same, and here you have 6 sine of t minus 24 exponential function to here 2 of t. So what is the solution? Of course, it's 6 sine of t. So the solution is going to be with y sub 1, it's going to be 6 cosine of t. Then we're going to add for the second one, you see this here, it's this non-homogeneity here, but we have 24 with the negative there. So That means 24 times y sub 2. And that's the solution we expect. So if we know the parts, then we know the sum. That's kind of the idea. All right, so let's do, what if I have this differential equation and I know the particular solution. Um, can we get a general solution? Okay, find a general solution. All right, so we can do the auxiliary equation, and then R gives me plus or minus 1. That tells me that the general solution to the homogeneous case that is associated with this differential equation is going to be C1 or C sub 1, the arbitrary constant times exponential function with t. Yeah. And the second arbitrary constant times the exponential function with negative t there. Right. So the general solution now we're looking for is a particular solution plus y sub h. So the idea is not complicated. It's straightforward in understanding, and and just go through the particular solutions. And if we have IVP, we'll just solve and using these initial conditions. So let's do more. Let's say you have this differential equation. And I have on the right side this polynomial and this exponential function. And I'm given that the particular solution is this. So this is given. And find the general solution. All right, again, so we go r squared plus 11r plus 18 or 0. And factor this, you get r equal -9 and -2. Two distinct real solutions. That means for the homogeneous solution, it's going to be some arbitrary constant times e or exponential to r1, which is -9. And now you know how to do this. Second constant times the other exponential function with r2t, which is -2 there. All right, so once we have that, now we can so x, yeah, so let's make sure since we have x on stated as, yeah, once we do a lot of examples with that, with t's, just kind of overlook that. So yeah, so we have here x, like, so it's kind of f of x, not a f of t. So here, to make sure these match. All right, so the particular solution is this. The general solution to the homogeneous case is this. Okay, I picked a nice example for you here before we keep going and solve different examples. Let's give you here an interesting question. Um, can um, this method be used here? And of course, this method stands for undetermined coefficients. We revisited, and of course, here we're just using superposition principle to look at multiple parts. Can this method be used here? And this is similar question that was done in the past to make sure we're not trying to attempt to use undetermined coefficients to a case that is not suitable for it. But this one is interesting. Let's look. So this is no issue. Now let's look at this right-hand side. That looks fine. That also looks fine. Then we get to this and we're like, what do you think? Remember, the talk about is you have polynomials, you have exponential function that E is base, you have what else? You have cosine and sine, and you have their products, right? We didn't say some exponential function base 15. So here the question, can we do this or not? So yeah, so I think if you think about the idea of 15 power t, it can be written as e, and I need something that cancels with it is natural log of 15t, right? If you do this, these are inverse of each other, will just give you that, right? So now with the power rule, it's t times natural log of 15, which is exactly just like natural log of 15 times t. So the answer is yes. We have what we're looking for here. Okay, so let's say you're not given the particular solution. Let's do that example. Let's say we have this differential equation. Okay. And we need to find the general solution. So find general solution. Let's look into r squared minus 1 equals 0, r equals plus or minus 1. So then we know this one is going to be this. All right, so what is yp? It's not given. So based on f of t, which is the right-hand side, I can say that this must be some linear function using at plus b or a sub 1 t plus a naught there. Okay. Then we know the method is to find first the second derivative, whichever are needed, and you're going to use them in substitute back into the equation to determine the coefficients. All right, so that's next. And when you do this, you would get this part. And that gives us that a sub 1 is 25, and a naught is -10, and so the general solution to this differential equation is given as this. All right, you want more? Let's do more. Why not? Let's say we have now in terms of theta, let's make it interesting. So we'll expect theta to be here. Okay, so to simplify, I'm just going to write it now this way. But I know what's up. Okay, so we go to the differential equation. We can change or reduce to this auxiliary equation. And that gives us two complex conjugates. All right, so comparing them. Alpha is this, yeah. Theta is this, yeah. So S is going to be 0. And y of t is going to be C1 P alpha, which is -11 theta, cosine 1 theta. Let's see, 2. All right, so this is kind of the particular solution. Let's see.